So I want to start out by congratulating you guys, because you must be the bravest people at NDC, coming to a crypto talk just after lunch. So thanks for that. The goal of this talk is not to dive into like how AES or some other encryption algorithm works internally, but rather talk about how to use, or more how to not use, encryption. So, quickly about me. I work as a developer most of the time, but I also do security testing. I do some bug bounty hunting, and I'm also the creator and maintainer of Retire.js, if anyone has used that. And I'm head of OS Norway, and also I'm not a crypto expert. I couldn't design an encryption algorithm if someone asked me to, but I know a bit about how to use it, because I've studied it for some time. Bruce Schneier says, anyone from the most clueless amateur to the best cryptographer can create an algorithm that he himself cannot break. And this is something you should remember. Never ever try to invent your own encryption algorithm. It's super hard. And the people who are actually designing algorithms, they're usually like, they build something, then they ask someone else to review it, and then they find all kinds of flaws, and then they go back and forth like this forever. So don't invent one yourself. If you want to learn more after this talk, you should go do these crypto challenges. These are super good, and you can learn a lot of the stuff that I'm going to show you by doing these, and a lot more than that as well. I'm going to use a bit of code throughout or later in the session. This is just some JavaScript stuff that I use so that I can do stuff like this. I can have a variable with a string, secret message, and I can generate a key which is 16-byte, and then I can do some encoding and stuff. That's just to make things a bit faster when I do the demos. If you don't find these functions in regular JS, it's because they're not there. But let's start. So first, a couple of words that we need to know when we talk about crypto, or the words that I'm going to use. Like plain text, that's the message that we want to send, the actual data. The ciphertext is the encrypted data. We have a key which we can use to encrypt or decrypt or sign. We have an IV and nonces. Those are basically salts, if you think in terms of passwords. Those add noise. Symmetric encryption means we encrypt and decrypt with the same key. And asymmetric encryption means we have a public key, which we can publicize anywhere, and then we have a private key that we ourselves hold. And then someone can encrypt the message with a public key, and only we can decrypt it. And then the same thing holds for signing. We have either symmetric or asymmetric signing. So why are we using crypto? Well, there are a couple of things that we want. We might use it because we want confidentiality, so we want to be able to exchange secret messages. We might also want to make sure that data hasn't been changed or data can't be changed, and we also often use it for identification. Typically, we sign tokens and we pass those around, and those kind of prove that we are who we claim to be. The next guy I'm going to quote is a person called August Kirchhoff. And if you see when he was alive, it's quite far back. But what he said was a crypto system should be secure even if everything about the system except the key is public knowledge. That means that if you have an encryption algorithm that doesn't take a key, it's not an encryption algorithm, it's encoding. So the key is the thing that's going to protect us, not knowledge about the algorithm itself. So all the algorithms that we're using today, like AES and all the other ones, of course, everything about how they work is public. It's the key that protects us. When we're going to create this key, we need to have a secure random generator, not something like this. But people are failing at this. So there was a couple of researchers that were looking at hard drives, and they figured out that some of these self-encrypting hard drives, they're not doing it in the right way. So one of them was actually, it was supposed to generate a big key, but that key was actually a small key repeated 4 times. So the actual entropy of it was like 32 bits instead of what we normally would want, which is like 256-bit or something like that. Another thing is, for instance, if you're using the non-secure random functions, like this is the one from Java, if you get 2 ints from that random, like you ask it, give me an int, give me another int, and then, or actually give me a long, because a long is 2 ints just appended to each other, then you can reverse engineer the state, the internal state of the random function. And there's even some GitHub code for it, where you can test it yourself. I played around with an application. This is quite a few months ago. I was trying to start an application in Docker, and the application wouldn't start. And I was like, what's going on? Why won't my application start? And it turned out this was a web application, and it was trying to generate a key for sessions. But the Docker container didn't have any entropy. It didn't have any random source. So it was just hanging, waiting for more random so it could actually seed and start the application. So that was a problem. It's not a problem with Docker anymore, but it used to be. Like, you couldn't get any random in there. And this has also been a problem with devices like Wi-Fi routers, where they would generate like these, instead of every router coming with security disabled, they would have like these default passwords. But some of them, they were generating these passwords in the wrong way, and so they were easily crackable. When we talk about like the length of a key, we often end up talking about the birthday paradox. So if there are 23 people in a room, that's enough to be quite sure that 2 of them have a birthday at the same time, which is kind of counterintuitive if you think about it, because like 365 days, you would think it was more around like half of that, not 23, which is fairly low. But the thing is, we have to take into account that there are many things that has happened already. So not only can you have the same birthday as this person, but you can have the same birthday as every other person in the room as well. So if we try to sort of calculate it, it looks something like this. And it's fairly close to the square root. So we often use the square root as an approximation. And this means that if you can choose from 10,000 values, you're going to get a collision after around 100. And if you have a key that's 2 to the 64, you're going to get a collision after 2 to the 32nd, which is also quite weird. This is me just calculating numbers between 0 and 999 and seeing how many times do I need to do it before I get a duplicate. So you see, the average I got here was 116, and not 100. So, but the actual number is a bit higher than 100. But I found duplicates somewhere after 11 here, after 27, after 10, and sometimes I have to go higher than was expected. And I can do this many times. The last number there is just the average. So I can just keep going, and it stays at around the same place. So I'm just doing numbers. So once we have a key, now everything is super good. Like, we create a master key, and everything is fine. And then we have this. This tells us something about the keys that we have and how we should handle them. If it's easy to get the key, then it doesn't matter if we encrypted stuff really well. So if we encrypt a lot of stuff and put it in the database, and we also put the key in the database, SQL injection will extract all of that, and it's back to 0. But OK, so let's start trying to encrypt something. So we're going to start with an attempt at defining what we want. So given a ciphertext, it should be impossible to find the plain text. So if I want to communicate with one of you, it should be impossible for everyone else to figure out what's going on. The first thing we could do is we could share some keys up front. So this is a one-time pad from Wikipedia. We could also, and this is kind of used to substitute letters, but we can do it in a more computer-friendly way. So we can generate a random key and share that key, so only we have copies of it. And then we can XOR whatever we want to send with this key. So we just XOR the letters together, and then decryption is the same. We just XOR the ciphertext then with the key. So we have a plain text, which is a message. We generate a key, and we take the values that's or the hex values of the letters, and we XOR them, and this is the ciphertext that we get. That looks nice. Okay. Is there any problem with this? Well, first let's look at how XOR works, by the way. So we do it bit by bit. So if A looks like this, and a lowercase a looks like this, and space looks like this, so we see the difference between the capital A and the lowercase a is actually just the third bit is 0 and a 1. And the space character is actually the exact same thing. So if we XOR an A with space, we get a lowercase a, which is quite funny. And we can do the same with all the letters, even these crazy Norwegian letters that we have here. Works for them as well. And there are some rules there as well. If we XOR a letter with 11111, we get the exact opposite. If we XOR it with 0, we get the same thing back. If we XOR the same thing with itself, we get 0. And you can switch them around. It doesn't really matter. And also, if you have one thing that's XORed with something, and you XOR that with one thing that's XORed with the same thing, the two A's here in this case, they cancel each other out. And so the end result is B XORed with C. This sounds a bit, well, why am I talking about this? We'll get to that in a second. Because the one-time pad, it's confidentiality-wise quite secure for a single message. It's super hard to break it because, I mean, the key that we are using, it could mean anything. Like, there are a lot of different valid values that could come out once we do the XOR. It could be secret message, as I showed just earlier, or it could be like a Britney Spears song with Hit Me Baby One More Time or whatever. It doesn't matter. It could be anything, so we don't know. But the problem is we can only use the key once. That's not a nice thing for an encryption scheme. That's why it's called a one-time pad. And how do we exchange the key? Because the key actually has to be the same or longer than a message we want to send. So we need to have some way of actually transferring these keys. And for like old encryption systems, they used to have these like long paper things where with the pads in them, and they could transfer them up front, and then they would have a secure messaging system. But this is not very computer friendly for us. Why can we only use it once? Well, if we have a plain text and we XOR it with the key and we get a ciphertext, and we do the same thing with another plain text, what happens if we XOR the two ciphertexts? Well, the keys cancel each other out, and what we end up with is the one plain text XORed with the other. That doesn't work well. And if you have a lot of these, then you can start looking at these and combining them, and you'll actually be able to get back the original data. That's one of the tasks on these crypto challenges that you can play with. Also, if I know one ciphertext and one plain text, I can XOR them together, and then I get the key, which also isn't a nice feature. And yeah, if the message is longer than the key, then I would have to repeat the key, and then I'm actually using the key more than once, so that doesn't work. But, all right. There's also another problem here. If I can submit data to a system and have that system encrypt it for me and get the encrypted thing back, well, I could just send in a bunch of zeros, and I would get the key back, which is also not a nice feature. But for sure, no one is doing this, right? Unfortunately, that's not true. There was an app called NQVault, which was, I think, an Android app. It was used, it had lots of downloads. And it was supposed to encrypt everything you had on your phone. But first of all, it only encrypted the first 128 bytes of each file. And the way it did it was, it took the password that you entered, and it took the hash code of that, and it did an AND operation, which means it reduced it to a single byte. So now you have 256 different keys. So it's actually easier to brute force the key than to brute force the password. That's not a nice feature. So all right, this doesn't really work. Let's try to find a better definition. So given a ciphertext, it should be impossible to find a plaintext. We want to stick with that one, but we want to have a reusable key, one that we can use more than once. And we also want to be able to have a plaintext that's longer than the key. And there are a couple of ways we could go. There are basically two types of ciphers, or actually more than this, but two main types, stream ciphers and block ciphers. In a stream cipher, we generate a key stream from a key. So we take the key as input, we generate a long key from it, and then we can do exactly as we did with the one-time pad. We kind of just XOR stuff together, and then we get some output. One example is RC4, but that's not something we should use anymore because it's been provably broken. It has a tendency to have one of the bits be one more often than a 0 or the other way around, and that's enough to break it. It does support having a plaintext length larger than the key size because you're sort of stretching the key out. It does, however, kind of leak the plaintext length. So if we look at this, this is a voting database where we have 4 different votes, and I'm pretty sure you can figure out who voted no. So I encrypted all of them with the same key. All right, so let's encrypt them with different keys. Well, you can kind of still figure out which one voted no, because it's shorter than the others. All right, let's look at block ciphers instead. So the way block ciphers work is we split the data into blocks of a given size, and we encrypt each block separately. So AES is an example of this, or DES or triple DES is also an example of this. The first way we could go was something called the electronic cookbook mode. So we take our plaintext, and we have our encryption function that takes a key, and then we split the plaintext into blocks, we pad the last one, we run them all through this encryption function, and there's our ciphertext. And when we want to decrypt it, we split it back into blocks, we take the decryption function, taking the same key, run them through, remove the padding, and we have our plaintext back. But the problem is, what happens if 2 blocks are equal? Now, AES, for instance, is a deterministic algorithm. There's no randomness involved. So if you have the same key and the same plaintext, you get the same ciphertext block, which means if you encrypt the Linux Penguin, you can easily, from just studying the bits, you can sort of reverse engineer the picture that's behind it. All right, so what is the natural next step was to find some other modes where we kind of add some noise. This is where the IV comes in. So there's something called CBC, cipher block chaining mode. So we start out the same way. We split up and we pad, but then we introduce this IV. And what we do with the IV is we XOR it with the plaintext before encrypting. And then we take this first block of ciphertext and we XOR that with the next one. So we kind of propagate the noise that we got from the IV throughout. So we go ahead like this, and we get our ciphertext, and we usually then send it together with the IV to the one who wants to decrypt it. And it goes like this. So we run it through the algorithm, we XOR it, and we get it back, and then we take this thing, and it works like this. Fairly simple. Now we've propagated some noise through. It should be, so now we won't have the Linux Penguin problem anymore. But there are some other problems here. So on the left-hand side here, we have the IV. That's the I0, I1. That's the individual bytes of the IV. And on the right-hand side, with the C, you have the ciphertext bytes. And when we decrypt this, we first get what we call an intermediate value, and then we XOR it with the IV, and out comes the plaintext. Fairly simple. So if we change a single bit up there in the ciphertext, because of the way these decryption algorithms work, that will completely change the intermediate value. It will become something completely different. And thus, when we XOR it with the IV, the end result is probably going to be garbage. However, if we change a single bit in the IV, we will only change a single bit in the results. And this is something we can use. So let's say we had something looking like this. So this could be like a signed cookie, or an encrypted cookie, I'm going to say, an encrypted cookie with JSON. So it's a user ID 5. If we change the 11th byte of the IV, we would change the outcome of the 11th byte here in the plaintext. So if we remember the XOR stuff, we could say, okay, so the letter 5 has an ASCII value of hex 35. So we know that I11 and V11, that becomes 35. And we want it to become a 1 because we want to be user with ID 1. That's usually the admin. So we can calculate it and figure out that what we want is just to take the original value up there, we XOR it with 35 and 31, and thus it becomes 1. So, but this is boring to just see on a slide. So here I have this nice little application where I can log in and out with a password, but I can only log in as Homer because that's the only guy I know the password for. But there's a cookie here. Sorry. And okay, so there's something called session 2 and something that looks kind of like some encrypted stuff, at least base 64. So we could go ahead and we could try to grab that one. So we can say, okay, I'm going to split on the semicolon sign, take the first part, split on the equals, take the second part, and that would give me that value. Okay? And then I can take that and I can base 64 decode it. So this is the functions I talked about earlier, and then convert it to a byte array. Like this. I'm going to store that in a variable so I can play with it. So now I have the ciphertext as a byte array, basically. So now I'm going to change the letters. So I'm going to take the H up there. Maybe this is a bit too small. I'm going to try to make it a bit larger. So I'm going to take the H up there, and I'm going to XOR it with the A. But I'm going to first XOR it with an H to get it down to 0, and then with an A. And then I can do the same thing with the next one, because I want to become the admin, of course. So I can go ahead and the M in admin and Homer is at the same spot, so I'm not going to touch that one. I'm going to change the 12th one and the 13th one. So just doing the same operation all over again. And then I'm going to pack it back into the cookie. Like this. I'm going to take I'm going to set a new cookie called session2, so I'm going to overwrite the old one. I'm going to take this array that I now changed, and I'm going to create a string from it, and then base64 encode it. And when I now refresh, hopefully, I become the admin. So I've changed the contents, and I wasn't supposed to be able to do that, I would guess. So that's not exactly what many people are expecting when they're encrypting stuff. Like, okay, so we can change stuff. That's not good. But encryption isn't the same as signing. That's why we have two different things called signing and encryption. And encryption doesn't imply signing in many cases. Not for this one-time path either, because we could just flip bits and that would flip the end result. All right. When we're padding this is also interesting. There are many ways of padding data to make it compliant with the block size. One of the most common ones is called PKCS7. And we basically add, let's say we needed to add 7 padding bytes. Then we set all these to 7. And if we need to add 6, we set them to 6. And for the last thing, if the plaintext actually is at the block size, we need to add an entire padding block, because or else it wouldn't be able to separate if the P7 here was a 7, and it then would think, oh, I need to remove all the padding, and it would be wrong. So then we need to add an entire padding block. So why is this interesting? Well, a lot of frameworks, if you mess with the padding, so here it says there's supposed to be a 3, and according to this, then there should be 3, 3, 3. But here is 3, 10, 5. And then we will typically get an exception. So the decryption function will say, hey, the padding is wrong. I tried to remove this, but the first one was a 3, the next one was a 10. That doesn't make sense. And we'll get like a padding is invalid or something. And this is actually enough to decrypt the data, because we can abuse it. So again, I have the same setup. I have the IV on the left and the ciphertext on the right. But now I know nothing about the values here. So that's why there are question marks. So first, I'm going to take a copy of the original IV up there, because that's the original IV that was used to encrypt this stuff. So I'm going to take a copy of it down there, and then I'm just going to randomize, put a completely different IV up there, which is very likely going to cause the end result of the decryption to be garbage. And then I'm going to get a padding error, because it's likely not going to be a valid padding. The thing I'm going to do next is I'm going to start the last byte of the IV. I'm going to start flipping it. I'm going to start at 0 and then go all the way up to 255. At some point, I will get a valid padding, because then this thing will be a 1. So let's go ahead and do this. I'm sending requests to the server, sending lots of requests to the server. And you can see it's going up, it's going up, it's going up. And at some point, it will tell me, hey, this was a valid padding when I get a 1. Sometimes it happens early, sometimes it happens at all the way towards the end. We'll see how lucky we are today. It looks like it's going to be all the way towards the end. Okay, so there. If I sent in DA there, I got a 1. So now I know that this is a 1, and then I can XOR that with DA to get that value. And then I can XOR that value with this value to get this value. I know this is kind of hard to grasp just after lunch and everything, but that's the way it works. So now I know that it's a 3, and I know that this one was padded with 3, the original message. Then I change this one to become a 2, and I try to brute force the next character. To change this one to become a 2, I simply have to take the last byte and XOR it with a 1 and a 2. So we go back to 0, and then we go to 2. And then I can start brute forcing the next one. And this is speeding up now, so it's not going to be as slow as it was for the first one, because it's going to take a bit of time to brute force all of them. So the cool thing about this, if you've seen a movie where they're attacking something and they come up to a door and they have this card that they're sticking in, and they're like, oh yeah, we're gonna get the password back, and they get that one character at a time. Well, this is the exact thing that's going to happen here right now. Look at this; it's finding one letter at a time. And you can see now it's speeding up, so it should be. But look at the request count over there. So I would have to send a lot of requests to the server to do this. And soon we will have the very boring message that was actually encrypted here. The funny thing is that this is actually running in the browser right now. Almost there. And there we go. So stolen secret, that was the plain text. So by using this, we were actually able to get the original message back without knowing the key, just by abusing the padding. So why is this important? Well, there has been bugs around this. Like in 2010, there was this problem with the way that files were being downloaded from, or actually Ajax and JavaScript files were downloaded using ASP.NET. The thing is, you can actually use a padding oracle also to encrypt messages. So you could change this to be the file that you wanted, for instance, webconfig, and you could download that by using this error. And there's been a lot of them in TLS or SSL as well. Example here, Poodle, which is padding oracle on downgraded legacy encryption. So there's padding oracle again. And there was one last year, which someone called Lucky -20 or something, but it was also a padding oracle problem in TLS. Okay, so let's kind of try and avoid these padding oracles. So let's do something like this. Can anyone tell me what's wrong with this code? Makes sense, right? Okay, so if the decryption fails, we get a padding exception, and then we return not found, and that's the same thing that we're going to... Yeah. It takes a different amount of time, because if the value is correct, we're going to look it up. If it's not correct, we're just going to go straight down here. So we have a timing problem. This was actually a timing problem, the one I just talked about. And there are a lot of other of these side channels, as we call them as well. It could be response time or computation time. It could be CPU usage. It could be power consumption, if you can measure power consumption. That's something they often do if they're attacking like chips on smart cards or things like that. It could be electromagnetic leaks. It could be the size and more stuff. So here's an example of a size problem. In this case, the headers of an HTTP request are compressed. So if we are, as an attacker, can make someone's browser do a request and we can observe the length of the data as it's flowing over the wire, like let's say we're sniffing a conference network, we will see a difference in the encryption here, or actually in the size, because of the compression. So the first one will say J session equals A, and then the next one says J session equals B. But if we get it right, it sort of shrinks a bit, and that's enough to also decrypt data. And then there's this thing I found the other day. I'm going to zoom in a bit. By measuring the target's electromagnetic emanations, the attacker extracts the secret decryption key within seconds from a target located in an adjacent room across a wall. That's kind of scary. Just by like measuring radiation from your laptop, they can get the encryption key. All right. But what if we kind of could get also integrity from encryption? There is something called authenticated encryption. And what we're doing when we're using authenticated encryption is that the encryption algorithm also generates a tag or a MAC on the data, and that proves that it hasn't been tampered with, so that would foil our previous attacks. And examples of such algorithms are AES-GCM or AES-CCM. You've probably seen AES-GCM used on the web now. It's often used in TLS connections. But it has some weird properties as well. So both GCM and CCM are based on something called AES counter mode. And AES counter mode works like this. So we take the plaintext and we generate a nonce, a number to be used only once. We split it into 3 blocks because we're going to need 3 blocks in this case. And this is the counter. That's why it's called the counter mode, because this essentially becomes the counter. So the first block is of 0, 1, 2, etc. And then we encrypt these counters to generate a key stream. And then we remove the stuff that we don't need from the key stream, and then we XOR them together, and we get the ciphertext. And we send that off. And then the receiving party can do the same thing. It takes the nonce, adds these numbers, and encrypts them. And you can see it happens in parallel. That's why a lot of people like GCM, because you can encrypt the individual blocks in parallel. In CBC, you always needed the result from the previous operation. So it's not parallelizable, but this one is. And then we have the key stream. We drop the stuff that we don't need. We XOR them together, and then we get the plaintext back. Now, the problem here is what happens if we reuse the nonce? Then we get the same key stream. And then we're back to the one-time pad, right? If we XOR 2 things together. So this is how GCM actually looks. The stuff that I just talked about is what's going on up here, but there's some stuff going out here and some stuff which takes these, which generates this tag that's going on down here. And we get a tag at the end. So this is what kind of GCM adds to CTR. And there's been problems with this as well. There was something called the forbidden attack on GCM in HTTPS, where it was found that some implementations, they would reuse the nonce from time to time, and then it all falls apart. The next thing is asymmetric encryption. So we're just going to briefly talk about that. The most common one that people are familiar with is probably RSA. RSA actually has this property that if we're going to take a plaintext, we can only encrypt something that's lower than the key length. I think it even has to be a bit shorter than the key length. But usually the way we do this is we generate a symmetric key, because symmetric encryption is a lot faster than asymmetric encryption. And then we encrypt the data with this symmetric key, and then we encrypt the symmetric key with the RSA key. So this is the way HTTPS or TLS works. This is a good algorithm for doing that. This is not so good, but this is very, very common still. And if you ask the cryptography professor, Matthew Green, he says, PKCS 1.5 is awesome if you're teaching a class on how to attack cryptographic protocols. In all other circumstances, it sucks. So, all right, we shouldn't use that anymore. If we're going to try to use, for instance, CBC, we need to add integrity to it. So we could do something like this. We could take our ciphertext, we can encrypt it, and then we could sign it with a signature algorithm, and then we can send that over to the client, and then the client should check the signature first, and then decrypt it, because then the signature will fail if you tampered with it, so we wouldn't have a padding oracle. It's super important to check the signature first. But all right, let's talk a bit more about signing. So the first thing to note is don't invent your own signing. There's a lot of people who are trying to be clever, and they're doing something like this. So the signature that we're going to have is we use MD5, and we take a secret key that only we know, and we take the message we want to sign, and we just concatenate them together, and we generate a signature. It doesn't matter if it's SHA-256 or if it's MD5. It doesn't really matter. Even putting the secret at the end is not a good thing. This is why we have something called HMAX. We should use that instead. An example from Flickr, they had an API back in 2009 that was using this construct of secret plus something and then MD5. And they had some other issues as well. If these were the URL parameters, it would do a normalization of that. It would just remove the ampersands and the equal signs and shove them after the secret, and then that's what would be signed. The problem is that according to this algorithm, these two are the exact same, because was it a B with this value, or was it actually bar 2, and et cetera, et cetera? It doesn't know. To briefly explain how this works, imagine we have some data and we want to sign it. So the purple stuff here, that's the secret that only the owners of the site know. And the blue stuff is the data. So also MD5 is block-based. So we split it up into blocks. We pad the last block, and then we run the same function with the previous thing as input. So first we start out with what's called the S block, which is like a starting value for MD5. And then we run the function on it and mix those two together. And then we take the output of that and mix it with the next block, and then the next block. And we end up with this result. The problem here is you can do something called the length extension attack. If you, for some reason, wanted to hash something that incidentally had the same padding value here. So let's go back a bit. So if this thing has the exact same padding value here, these things, the first part here, is equal. So if we have the output of this, we can simply use that here and add new data and add a new valid padding. And thus we've added stuff to an already valid signature. So this is pretty bad. So use HMAX if you're going to sign stuff with a symmetric key. If you're going to do it with a private key or an asymmetric signing, you could use elliptic curve cryptography, or you could use RSA. If you're going to use RSA, use decent padding scheme and not this PKCS 1.5 again, because that's broken there as well. Signatures are used in many different places, and one of them is in XMLs. So I'm going to briefly explain how XML signatures work. So we have this token, and we're adding a signature. And a signature consists of a signature tag, and there's a signed info tag inside it. And the signed info is basically saying how this thing is signed. So first it tells us which canonicalization method is being used. That's to ensure that the verifier and the signer sees the same XML, because XML can be in a lot of different ways. Like you can have an empty tag that's a start tag and an end tag, or you can merge them together and have the slash at the end. You could have white space between tags and not, etc., etc. So that's what canonicalization is about. And here we say the signature method that we're going to use is RSA, and we're going to use SHA-1 as the hashing algorithm. Then there's a reference, and the reference tells us which element is actually signed. So in this case, it says something with an ID of _0, which is the username up here. So this one has an ID of _0. So this is the thing that's going to be signed. And then it tells us how that one is canonicalized, and then it's being hashed. So here we say we're using SHA-1 as the hash function, and this is the hash of this element. And then what we're actually signing with XML signature is this signed info element. So we can have multiple references in here, and then we end up signing this. So we're kind of signing a hash of something that's already a hash of something else, and it's kind of weird, but that's the way it works. What's wrong with this code? Who can tell me what's wrong here? It's very obvious when you know it. It's not necessarily if you haven't seen it before. Yes? It's not a timing attack in this case. Yeah, we'll get back to that. Yes? Yeah, we'll get back to that as well. The thing here is, it says valid, there's a hint here, validate all the signatures. Yeah, what if there are no signatures? It's going to pass, right? Okay, so we need to be clever. Let's check that it's actually signed and validate all the signatures. And then we're going to grab the username from this XML that we had. But this is wrong as well. And now we get to what you two guys were saying. Are we actually signing the stuff that we're using? What happens if we move this username underneath some weird tag that we don't care about and introduce a new username up here? Well, this thing is still going to be a valid signature of this element. It doesn't care if it has been moved. It just looks for something with the ID of _0, and it's there. So this is still a valid signature of this element, but this XPath function at the end here will actually find this one. All right. Maybe we can try to do that as well. So I have a sign-in button here, and it logs me in as Homer Simpson. Okay, that's not very interesting. What did it actually do? Well, let's try to look at the code. We'll see there's a form, and in that form, it's sending in a signed XML. So I'm just going to do like this, change it to text. For some reason, it's actually better to edit it here, and I'm just going to add a new username field with admin and close that. And I'm going to add an A tag around the original one. Let's see. So just a random tag that I don't care about. And now I'm logged in as admin, because the signatures are still valid. I'm just not signing the thing I think I'm signing. Okay, so this all sounds a bit, yeah, but would anyone actually make this mistake? Turns out, yes. Some researchers from Germany, they looked at a lot of the different SAML libraries some years ago. This is what they found. They looked at 14 different ones, and 11 of them had these problems. For some of them, you can actually just remove the signature, and it would work. You could just become anyone you wanted to, which is pretty bad. Now, what's wrong with this code then? In this case, it's a little more subtle. This is a timing attack again. So where we have a signature that's been generated, and we're comparing it with something that looks like a... we're comparing each character, and yeah, hopefully this will return something that makes sense. And this is typically how the equals functions on strings work. Something like this. And in this case, we will have an early exit here at the first invalid byte, the first one that doesn't equal. So we have a problem. Okay, so let's change it. So we're going to put the Boolean outside here, and then we're going to change it in here, and then we're going to return it so we're sure that we run through all of them. But it's still wrong. Why is that? Well, because we have something called JIT, just-in-time compilation. And it's actually going to see this. Well, if this one changes to false, it's never going to change back to true. So I might as well exit. Damn it. Okay, so we need something called constant time comparison. So here's the XOR, and we're doing some OR stuff here. And you don't have to understand this. It's just the way it ensures that the JIT won't come in and mess things up. So the next thing we could think about is JSON Web Tokens, because those have become quite popular. So typically, when we're using a JSON Web Token, we can encode it in many different ways. In this case, we're using HMAX SHA-256. So we have a header that tells us which algorithm is in use. So in this case, that's HS-256, that's HMAX SHA-256. And the type is JBT. And the payload is logged in as admin, and there's a timestamp. So we base64 encode these two, and we concatenate them with a dot in between. We sign that, and that becomes the signature, which we also add to the end. So everything is base64 encoded. Looks fairly nice. The problem is the implementations of this have not been at the best quality sometimes. So there was a vulnerability in many of the different JBT libraries. One thing is that the JBT standard, it supports an algorithm called none, which means what it says. There is no signature. So if you could send in a token and just set it to none, then you could once again become whoever you wanted to be. Another problem was that there was something called a type confusion, where you would send in something that was signed with RSA, but the attacker, if he had a copy of it, could alter the header to say HMAC. And the code running on the server side would then look at this incoming JBT token, and it would have a key, which used to be a public key for RSA, but because it got in a token and it says, oh, okay, so this is supposed to be an HMAC, and I have a key, so I'm going to use the key as an HMAC key and verify the signature. So it ended up using the public key, which was known to everyone, as the signing key, which means you could once again forge tokens. And also, there's been problems with this RSA 1.5 stuff that I've been talking about, which was about half a year ago. There was a problem with this library. And more recently, meaning a couple of weeks ago, this thing was issued, actually less than a couple of weeks ago, so it was January 10th. This thing was issued. It says there's some vulnerabilities in these token signing verification things in the Microsoft Identity tokens. And then I went on Twitter to figure out what is this thing. And I find this thing. So if you use identity model 5.1 with symmetric signing keys, don't miss this important security advisory. Okay, still a bit low on detail, but then we scroll down, which means you can truncate the JWT signature to force the comparison on only 1 byte. So you just stripped all of it and left 1 byte. And then we say, okay, so the length of this HMAX is obviously 1. And yeah, so you could sign whatever you wanted. So if we're going to use signatures, we should first verify that the signature is correct. Then we need to verify that the elements we expect to be signed are in fact signed. So we don't have this where we can move stuff around in the XML. And then we have to ensure that they're signed in the way that we expect them to be signed. So someone hasn't altered the signing algorithm to be something completely different. And then make sure we actually use the data that was signed. So circling back to Bruce Schneier, there's been a lot of discussion lately about, is crypto good enough, right? Do we have good enough crypto, all with the FBI phones and all the breaches and all kinds of stuff? And what he says is the math is good, but math has no agency. Code has an agency, and the code has been subverted. So this is actually what we've been looking at. Like, we've seen a lot of places where the code that's using the crypto is wrong. It's not the crypto itself, like it's not AES that's wrong, it's the way that it has been used. So, some recommendations here towards the end. Never ever invent your own crypto. Bruce Schneier is watching you. Use a crypto library and learn how to use the cryptographic constructs correctly so you don't make any of these mistakes. Use secure randoms, of course. And never, ever, 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 ever put the keys in source control. Don't put your keys on GitHub. They're being scraped all the time. If you do this, this could be your application. I'm going to zoom in. So we have a door with a card reader. And we have, what's going on here? I think I could squeeze in there. This is just like a piece of cloth that's holding this thing. And there's like a drywall piece or something. This is something I saw on my way to work one day. Don't let this be your application. Like, you have something really super secure in the middle, and then you can just easily circumvent it. To be fair to these guys, this was like a very temporary solution. A couple of days later, they had actually fixed it and attached these things in the right ways. So that was better. Given I have time, I'm going to show you one more thing. So this is a research facility, and then they have some papers that they want to allow you to download. And in this case, if we click this link, we're going to get to see this super cool research that they've done. If we look at the URL, which is a bit too small for you to see, I'm going to paste it down here. We see, okay, so there's a URL, and there's a signature, a long signature, which looks like some hex stuff. Okay, so what happens if we tamper with it? Let's change the last from a 2 to a 1. Ouch. Bad decrypt. What's this? You should know this by now. This is a padding oracle, right? This is a padding oracle staring us in our faces. Because it tried to decrypt something, so this wasn't a signature. It was, in fact, an encryption of the file name. So if we're nice enough to try to guess what the file name was, so this one is called paper 1. Maybe they have some unpublished research that we could steal. That's called paper 2. Okay, so let's grab this so-called signature. And we're going to, let's see. Let's just delete this for now. I'm going to hex decode that. So we get back a byte array. And we're going to change something. We're going to, okay, so we have to count. So like the paper, that's 1, 2, 3, 4, 5 letters. So the 6th letter, we're going to change that from a 1 to a 2, which means we need to change, of course, the 5th one, because that's the way it works. And we're going to say, okay, so I need to change that from a 2 to a, or actually from a 1, it doesn't matter, but yeah. From a 2 to a 1 to a 2. And now we're going to pack it back together again. So hex encode this. Okay, so now we have a so-called signature. And we're going to go back up here and going to change from paper 1 to paper 2. And we're going to paste our modified signature. And we get access to a new unpublished document. Because, yeah, signing in crypto and stuff. If you want to learn more, there's a long presentation called Everything You Need to Know About Cryptography in 1 hour. And it's 2 hours long. Some people you might want to follow, Matthew Green and the others here, do the CryptoPulse challenges. I'm right now trying to do them in JavaScript, but there are solutions out there where you can find solutions in Java and all kinds of stuff. But go look it up. Also, there's a really good book called Cryptography Engineering, Design Principles and Practical Applications by Schneier and these other people. That's basically it. So thank you for listening. Any questions? Yes, you'll get a microphone, just a second.
Thank you. Would the slides be available?
Yes, I will make the slides available.
Thank you.
Anybody else? I'll be here the rest of the day, so if you find me and there's something you want to know, just grab me and ask. Oh, gentleman over here.
I've got a question about communities. Basically, your different platforms, any specific sets of communities should be reverting to when you're starting to spot these types of issues. I see you had a list of individual names, but certain types of communities that are well known and respected to be able to follow.
I'm not sure. Maybe you'll probably find some really good crypto communities around universities, because a lot of crypto research is usually academic-based. Around this German university in Bochum in Germany, they have a lot of really good cryptography research coming out. The guy who found these SAML bugs and also one of these TLS bugs, he's also written a new test suite for testing TLS and trying to uncover these kinds of mistakes in TLS implementations. Google recently also released a tool for testing Java-based encryption, and actually, the guy who found many of the bugs that I've shown now, especially the PKCS15 bugs, he's called Bleichenbacher, I think. He's involved in that Google project. So you'll find some really smart people there as well. No more questions? No? Okay, you just adjusted your glasses, that's fine. Okay, thanks a lot. Enjoy the rest of the conference.